Hello, Velocity. All right. So there's a very good keynote this morning by Ben Rushlow about performance and context. Loved his takeaway that it's really the business context of performance is what we're trying to improve. And this is relevant to our talk as well. Our talk is about finding patterns in your performance and improving your performance. And we wanted to start with the same kind of concept. What's the context that we're talking about here? We've been talking to customers about performance for a long time. And our customers break down into a couple different groups. And one easy way to separate ourselves into categories is with this little Rorschach test that we have here. And so the question up there, what might this represent to you? And there's at least two ways that we see customers looking at performance in a modern context. The first context would be for a classical application. This would be an application that has a relatively static amount of infrastructure that's running your application. And so the intent for most of our customers running this kind of infrastructure is the business wants to define a service level. And then from the technology side, we want to measure how often we meet that service level. And because we have a fixed amount of infrastructure, we're going to see a response time that varies over time. So this would be the natural kind of curve that you would see, for a classical application. For an elastic application, you have kind of the same concept, but the meanings have become flipped. And so I think this is one of the most exciting things to happen in performance monitoring in a long time. Now, obviously, this is our idealized response time that we're talking about. Maybe that's not the true actual response time because we're working to improve it. But in this case, we're working to make that line flatter. So as a performance engineer, it's kind of interesting that the future of performance looks to be a perfectly flat line, right? So in this case, what's happening is it's actually our infrastructure that's changing. Our infrastructure is elastic. So as our performance begins to dip or begins to suffer, or as we see new loading characteristics, the infrastructure will be scaled up to meet that challenge, and then will be scaled down. So regardless of which of these camps you might fall into, and of course there are other varieties of these, but the context is usually we're either in a classical application looking to improve our service levels, and that's why we're working at performance engineering. Or for an elastic application, the performance itself is really what defines our cost structure. It defines how cheaply we're running our site, how easily we can burst to handle our maximum load, and business folks really like to see that kind of optimization. So I'll turn this over to Steve now, but this is the context that we want to fit in. So how do we go about it? Regardless of what kind of application we have, a classical application or an elastic application, how are we going to dig into our information and make our performance better in either of those contexts?
Thanks, Rob. So I myself was interested too. Rob first brought this up to me, and I was like, yeah, it's interesting how your perspective can change so easily based upon kind of how you look at things. And the keynote this morning was the same thing. What is it in context? And it can really change your answers quite a bit. So it made me think of something I saw a long time back from Harvard. I wanted to do a quick little test, quick little experiment we have in the house. If play along, it'd be fun. And normally in a presentation, you don't like people looking down at your iPhones and laptops. But for just a second, I want everybody here on this side of the room to actually focus on your device and not look up at the screen. And I'm going to show a picture to this group. 5 seconds. Go. 1, 2, 3, 4, 5. Okay, remember that picture. Same thing. I want you guys to now look at your phone. I'm going to show you guys a picture. 1, 2. Okay, remember the salient details. Now, just a couple of seconds of conditioning, and I'm going to throw up a third picture. And I'm going to ask you a few questions, and we'll see if we can come to an agreement as a group. Do you see the differences between the picture you saw and the picture that's up here? Yeah. So a couple of questions. One, who would categorize this as a caricature of a fairly young woman? Okay. Who would characterize it as a fairly older woman? Interesting. So how many would say she's wearing a necklace? And how many would say she's got a pretty big nose? So you see we get fairly diverse answers here based upon just 5 seconds of preconditioning, which I find is interesting because we find a pattern and our brains lock onto it. And I don't know if you noticed, but there's actually two pictures of two different women up here, and it takes a while, but if you really stare at it, you'll see them both. How many can see both women? All right, you see it. So here's the picture that I gave to the first group, if you're missing it, and here's the one on the second one. So it's interesting, and it's interesting to see how our brains work, because once we latch onto a problem, whatever it is, a performance problem, a scaling problem, we tend to really lock it down. So I want to do one more before we get into the depths of the analytic part here. So that was with preconditioning. What about no preconditioning? So I'm going to pop up a picture here, and I want to, as soon as you recognize this individual, I want you to raise your hand, but don't say their name. Recognize their name. Okay, you in the very back, who is this? Marilyn Monroe. Who is it? Who do you think it is? You thought it was Marilyn Monroe? What about you in the front row? No? Albert Einstein. Let's blow it up. Can you believe that? Now we can go through. This is actually out of MIT, but they actually took a picture of both of them. And if you're far enough away from it, it looks just like Marilyn Monroe. You blow it up, and it's Einstein. So, what's the point of all this? For the people in the front, that's what it looks like in the back. So the lesson here is we're not always as objective as we think. We still have these biological brains, and we get fooled sometimes, especially on pattern recognition. So with that, maybe we need to back up just a little bit and look at the scientific method, right? We kind of all have this built into us, but sometimes we can make mistakes. So now I want to get into the performance side of things. What do we do when we're actually diagnosing performance problems? Well, here's a typical conversation. Well, who's having the issue? Well, there's a few dozen users are complaining. Well, how bad is it? Ranges from 15 to 60 seconds. Are they all in a particular location? Nope, all over the country. And are the other users using the app okay? Yeah, average response time is 1.2 seconds. So overall, the health is good. And which is actually one of the interesting cases. Rob talks about, in the new elastic environment, we can do really well for the average, but a lot of times you still have performance problems that scaling will not help you with. And this normally, of course, isn't a conversation between two people. Normally, it probably looks something more like this, somebody hacking away on a computer. And to be realistic, it probably looks more like this, right? All right, so we wanted to take a closer look at this as we went through, and we really did a full redesign of our monitoring approach with Foglight as we rolled out our SaaS solution. And one thing we did is took a good hard look at this process of how you go about solving performance problems. And if you really stop and step back, you'll see that the human is on the left here doing basically hypotheses, guesses, like we saw in the conversation. Could it be this? Could it be that? And then we have the computer, the APM, the systems collecting all this data and then doing analysis on it, feeding back charts and graphs, and hopefully making conclusions. And this is a very iterative process. So as we looked at this, we started thinking, what if we could move that line just a little bit? Help draw some conclusions. Help the human kind of make quicker, faster decisions. And that's basically what IT analytics is all about, right? That's a big push. But then we also looked at the other side and said, what if we could move that line a little bit? Actually help ask some better questions. And so we charged down that path to see what we could do with it. So a couple of problems come up after we start to bring that up, and I'll let Rob talk to a few of those.
So this is one of my all-time favorite graphs that we got from a real customer. This is really shows the power of outliers because the graph at the top here is charting averages. And in this case, the customer is trying to optimize performance of their website. They're trying to fix the concurrency problem. And based on what they see in the top, it looks like the fix that they had didn't have any effect at all, positive or negative. But when you look at the bottom curve and you see what the actual distribution was, you can see there's an obvious place where the distribution changes. Now, of course, if we had standard deviation up here to go with our averages, that would give us another clue that the standard deviation had changed. But just looking at the bottom curve, you get an obvious, immediate sense of not only that there was a problem, but when the problem happened. So there was a configuration change. Configuration change was about 5:45. That's when the thread pool was changed. And changing that thread pool didn't have a huge impact on the averages, but it created a lot more outliers than were present before. This is very important to have a more fine-grained and refined view of performance. And in my opinion, everything that we're doing, especially in terms of elastic computing, really means moving towards a more fine-grained approach to tracking performance. If you are going to base your elastic scaling on averages, you're going to have a lot of problems. You're going to have a lot of false negatives. But in this case, we can see, because we're capturing and storing the discrete data, that we're not reducing this to statistical aggregates. We're trying to keep the raw data for as long as possible. Of course, if you can do that, then there are going to be additional benefits as far as being able to analyze that data later. We like to think of ourselves as really good at big data, and for obvious reasons. But where we've come from is it's easier to build the database than to understand it. So you get to a point where capturing the data, being able to mine the data, being able to query the data efficiently, that's not really where big data ends. Big data is an enabling technique, but really it's the outcome, the business outcome from that is so important. So by saying that we're going to forego averages, and by saying that we're going to forego purely statistical techniques, we're going to capture as many trace elements as we can, we create this big data problem for ourselves. The averages and the statistical models are very quickly reduced to something that a human can understand. Now, they may be misleading. That's the trade-off. If we want to try to flip the script on that and look at the raw data instead, then we have a big data problem. And that big data problem is not just how you capture and massage all the data, but really, what does it mean? What are the patterns? What are the commonalities? And how quickly can a human user come to understand those and also make them actionable?
Thanks, Rob. So coming out of that, I want to do a real-world example. So this is actually on a proof of concept I was involved in with our on-premise solution. I was calling Rob on the phone, doing different things. And so, if you've ever been in a technology proofing kind of exercise, you typically want to get in, show value quick. So it's a little bit almost like crisis management. You want to solve the problem quickly. So we're at this one particular company. As VP IT is saying, we got these user complaints. Overall, the averages are good, but we know there's a problem in the system. So we bring in our stuff and we get it all configured, and I go and pull a query of all the slow-running transactions, start looking for patterns, and really quickly pops up. Every single one of them's in an IE9 browser. And of course, we're predisposed to think there's clearly a problem there, right? So I'm happy. I go over and into the VP's office. It's like, we've fixed your problem, and we know what it is. It's some sort of browser-specific issue. And I'm expecting to, way to go, that was fast. I was pretty happy. But then he looked at me and kind of, well, that's interesting because IE9s are a corporate standard, and this is an internal application. And if anybody's not using IE9, I want to know about it. So I kind of tail between my legs, walked out of the room, said, okay, that didn't go too well. So, where did I go wrong? Did the scientific method fail me here, or what did I do? So, clear if you step back and think about it. I jumped to conclusions here. I had assumed that IE9 was the determining factor of the problem, but that was flawed. I made assumptions about the distribution of traffic that was incorrect. So this is easy to do. In my case, I was just trying to do something fast, but it's even easier to do if you're in crisis mode. Your system, your site is having a problem, and people are like, what's the issue? You tend to jump through these hoops pretty fast and look at patterns differently. And it's even easier to do if, like in my case, I was only looking at the problem data. I didn't compare it to the good data. So this happens in other disciplines too. I'm not going to waste any time on it, but I got some funny stories in both aviation and space industry where people get fixated on patterns and can do some crazy things independent of what the data is actually telling them to. So here I want to bring up what most people know, but we want to reinforce. Causality and correlation are related but different things. So we've got to be really careful about when we see a pattern inferring a reason from it. So it's easy in the heat of crisis to fall into the trap of believing what feels to be true. So I like this one. Some of you may have seen it. Here's the premise. Do Mexican lemons actually prevent highway death? This is actual data, and there's a very strong correlation between the U.S. fatality risk over time and the number of lemons imported from Mexico. Very highly correlated. Clearly not cause and effect, though, right? But let's look at something more complicated where it's not so obvious. There was a lot of studies as hormone replacement therapy got popular where the people doing them started to notice there was a lower than average incidence of heart disease among the women on this therapy. It became interesting. So it actually eventually got to the point they funded a much wider study. And they did a randomized control trial. And what's interesting is they actually came back to show that it actually slightly increased the risk of heart disease. Not substantially, but it was just there. So they're trying to think, well, how did these come up with such different answers? So as they looked through all the data, the detailed data, they figured out that this was a choice. So the women that were taking this therapy were from a different group. They tended to be from a higher socioeconomic group, tend to have better diet, better exercise, and better medical care. And those things were responsible for the difference, not the actual therapy. So there's a term for this. They call it lurking variable. It's a hidden third variable that causes the correlation. And we've got to be really careful on this, especially in complicated systems like the human body, like the computer systems that we try to manage. So let's get back to our performance problem. What if it had been a public-facing site that I had been troubleshooting that time, normal browser distribution? It probably would have been a lot more compelling, and I wouldn't have been laughed out of the VP's office. So one thing from experiences like that and others, as we tried to look at how could we do something that's more accurate, we started looking at different techniques. We found it's much more of an indicator to look at ratios of things in the problem, performance issues, and compare them to ratios in the problem and the total set of traffic to keep from making these kind of mistakes. So we had to give it a name. We call it differential analytics. So here's how it's defined. Deceptively simple, not third-order differential equations, no heavy statistical delta, sigma kind of stuff. I was actually going to throw up a lot of math and try to pawn it off on you, but Rob says, no, they might actually believe that's what it does. So it's real simple. So the first is actually what I was doing in the first place. We calculate the percentage of poor performing requests that have a particular dimensional value, such as used IE9 as a browser. And the second one is the percentage of requests that had this dimensional value, period, good or bad. And just by taking the difference between these two, it gives us a much more correcting number to play around with. So the higher this performance differential is, the more statistically likely that this dimension is strongly correlated to the problem you're experiencing. Okay, so let's run through a couple of examples to see how this works. So go back to my example. 100% of the poor performing requests had IE9 as a browser, true. But 100% of the requests had IE9 as a browser. So we do the subtraction, it comes out to 0. There's no correlation at all. And I wouldn't have been running into the VP's office. So let's look at a more realistic example. So if it's external, 100% of the requests that are performing poorly have IE9, but on a normal site these days, IE9 is running about 6% of your traffic if it's public. Okay, now we do the subtraction, 94. That's pretty highly correlated. It probably is a browser issue. Plus, it is IE9. So a more external realistic example is probably not going to be that cut and dry. So maybe it's 22% and 6%. So we still come up with a positive number here, correlation of 18. So it deserves some attention, but there's probably something else going on too. Maybe it's IE9 on a particular URL or on a particular server. There's something going on here. But it helps focus your attention on the things that need attention. So this is a really powerful technique to apply. Would have saved me some pain and just doing it manually. But when you do automation, it goes to a whole new level because the computer can run through these calculations so fast. So what if we do this same calculation for all the different device types we see hitting the site, all the different OSs, all the different locations, maybe even ISPs, so we can detect what ISP they're coming from, individual URLs, and then bubble up those to the top. We could even do it for method calls if we instrument the app server. SQL queries. Which SQL queries are driving this? Power starts to get pretty interesting. And what if we do the same for errors too? Look for highly correlated things that cause errors, not just slowdowns in performance. Pretty cool. So that's what we do with differential analytics. In a matter of seconds, we can evaluate thousands of possible correlations. We can do that for both performance and errors. And then by ranking these through, all the stuff that doesn't matter drops off, and you can focus on the top 3, 4, 5 things, and then really dive into what's going on there. So it really saves time and streamlines what I call that hypothesis phase that we go through when we're troubleshooting. Is it this? Is it this? Is it this? So, because we're basically guessing and disproving thousands of possibilities at a time and helping you focus your attention where it needs to go. So, I was going to do a demo here, but I saw the presentations from yesterday and the Wi-Fi, and it was brutal. So I grabbed a few screenshots just to make it simpler. So we have an app that we've broken in 2 or 3 different ways. And you can see up in the top left there, this one has some bad code in it. So we break the code and just very randomly, not very often, maybe 40 times an hour, it just goes into a pause loop and waits. And sure enough, real quickly, that thing bubbled right to the top as the worst offender with an 82% correlation. Now, there's a couple of different places coming into it that also were highly correlated, but this was the one that was the most correlated. Another example is we have a bad location. So we simulate coming in from a particular set of IPs through a particular ISP. And sure enough, it bubbles up to the top. And this particular ISP, we're picking on here, they didn't actually have a problem, but we simulated it. And you can also see that this is in Quebec, in Canada, so there's some lower correlating things. But you don't get distracted by those, you go right to the top. And then our browser example, here we're going to pick on IE11. But notice IE11, and we're doing it not just for IE11, but the whole category of Internet Explorer. So Internet Explorer is correlated at 40%, but IE11 is even higher correlated at 50%. And the platforms that you would see IE on the most, Windows 7 and Windows in general, are also correlated. So the technology to support this. The trick here is it's simple math, but it only works if you have the good transactions to compare it against. This is the equivalent of the randomized control study that we saw in the medicine. And it's heavy processing requirements to do it. You've got to store all the data, you've got to pull it back, and you've got to run this calculation. The simplification option we talked about early on is like, well, we don't really, if it went fast, do we need to store it? Maybe we can just save some room. That doesn't work here because you don't have it to compare against. You need the good transactions to be able to compare against. Otherwise, you don't reach that randomized control study quality. If you're only storing the aggregates, you're losing valuable outlier data. Anything else you want to say on that? You're the storage expert on.
Well, I think. It's on? Okay. Well, yeah, I think what kind of blew me away about this is this is maybe like the easiest MapReduce job you could ever write. Right? take some numbers and subtract them. I mean, when we first started going through this, I almost couldn't believe that it was that simple. And I think if you can switch to, I think, is it your next slide? No, the one where you're showing yes, this one here. So I think the thing to take away is that we're trying to move these bars, but we're not trying to entirely take over these areas here. We can aid with the hypothesis phase. We can aid with the conclusions phase. We're not trying to completely change that yet. If this sounds like an opportunity for machine learning, you're probably getting the right idea. But at this point, we're simply enabling the human to do a better job of what you were already doing. We, as humans, as performance engineers, we're automatically doing these correlations. It's part of how we listen. It's part of how we want symptoms described to us. It's part of how we want the bug even to be logged. And so there may be other hidden correlations here that the system can't find, but that you, as a human, actually know, right? But back to this case of, the human actually knows what infrastructure is running on their network and what versions of IE are used. That's an additional correlative element that you can bring into this. So what I really like about this technique is it doesn't completely eliminate the human. It allows the human to have a better sense of what correlations are indicated by the system, and then to combine that with other information that you know to give that larger, complete picture. So it's very much a way of cutting the effort of doing this kind of analysis. But the analysis itself, the analysis model, I think is a fairly familiar one. And as we've tried to relate, is something that we end up doing in the field, and our customers end up doing in the field.
Thanks, Rob. So that's how we try to push that line. So let's focus a little bit on the other line. How can we do some more analytics to help drive conclusions and make those cycles faster? So that was the other section that we tried to focus on. So differential analytics answers a very specific question, and we spent a lot of time thinking about it. And that question is basically, what are the most correlated characteristics of my problem requests? Well, there's a bunch of other questions we might want to ask and we're interested in. So just a few, like what requests are consuming the most database resources from an optimization point of view? How much time do I spend on the front end versus the back end? What app tier method is called the most frequently from a mobile device in the US by a particular browser type? Real quickly, you get into 5, 6 dimensions here. So the other thing we noticed is we looked at how people were using using our product is presentation styles are typically limited to 2 or 3 dimensions. It's just what graphs do for us. So like here's a scatter plot. We're really talking about 2 dimensions here. A lot of valuable data. You can see the outliers, but you're talking response time versus time here. Geographic map, same thing. Here, hit count by city. Okay, you could argue maybe 3 dimensions, latitude, longitude, and hit count. So how can we add more dimensions to answer these tougher questions? Well, one way is color, and we do this, but you start to lose some value. It starts to become harder to see those patterns. So traditionally, how is this handled? Usually it's through one of 2 ways. You either do screen-to-screen navigation, so you start with one 2-dimensional view, then you select some subset of that, and you go to the next view and add in another dimension, and you keep doing this through the different dimensions. Well, that'll work, but the problem is you kind of start to lose context, and your brain, as some of these studies have shown, once it's back, you kind of forget. It's just not in the forefront. So it's better to keep it all up in front of you at one time. So more commonly, we're starting to see the more portal style. Put all the information up, 20 different graphs on one screen. And that helps, and that's better, but the problem is they're all independent. So you can't narrow on one and see the effect on all the others. So one thing we built up for this release that we think is pretty interesting is we call it a visual filter chain. It's basically a portal, but each one is chained together. So as you select and go down one, the resulting data set is fed downstream, and everything's connected. So let me just show you. It's a little bit easier. So we start with our 2-dimensional scatter plot here. That becomes one of a portal, but as I go in and select things, everything downstream changes based upon what I selected there. Okay, so this becomes great for honing in on problems. Select some outliers, select a location, and you can mix and match these for different analysis types. So, for example, the question I just posed, you could build up one like this. Show me by device type, location, pivot on the methods, and then the different browser types. So here's a couple other examples just to kind of show you. I like this one. So here, instead of, we're used to seeing things charted over time, but a lot of times it's interesting to chart 2 different metrics against each other. So here, we're actual overall response time charted against the navigation processing time. I've heard a lot about navigation timing in the different sessions. So this is actually from navigation timing, the amount of time the request spent in the browser after everything was delivered, getting it there. So you see 2 distinct patterns here. A lot where there were some slow requests, but it was not waiting on the browser. This was took time for the server to get it there. And then there's this other class where this was very heavy on the browser side. In fact, this line is kind of like the theoretical maximum. This is when you're blocked. Nearly all of the time was spent in the browser. So we can zero in on these, go in and select this huge group and say, okay, well, what's going on here? And then see the distribution. Well, this is the distribution across the different browser types. And then we can drill into different traces to find out what is the URL that's being requested, where did it go in the app tier, and that kind of thing. Same kind of thing you can do here. Now we're going to look, instead of analyzing the front end, analyze the back end, in particular the database. So instead of charting the processing time in the browser, I'm going to chart the database time. And we see there's a bunch that are not database limited, but then there's this set, which is clearly database limited. The majority of the time of the requests was spent in the database. And as I go in and select a big clump of those things, we bring the top SQL statements that are responsible for that up to the top. And this happened 181 times. This is probably my biggest culprit as far as I'd like to go in and see if I can't make that run a little faster. And then you can drive down from here and go into individual traces, but it gives you a starting point. We collected data for so many years, and one of the big complaints we had, I was like, this is great, you have all this data, and I know my answer's in there, I just can't get it out. So help me start to look, because I'm like, it's the forest and the trees problem, but your nose is on the tree. So we tried to spend a lot of time saying, how can we give you a higher level view to help you go look at it first. Here's one more, just a time series scatter plot. Just like the example before, you can clearly see a configuration change happened here, and things got better, but we're still having problems. So now I can go in and see what's the next problem. And then just an example. So in this case, it looks like this authorization filter, which is a Java web method, is the problem. So now we can go in and see, okay, it looks like this guy is taking the vast majority of the time here at 9.31 seconds. So that's how we try to move that line around. And that's all I have. Questions?
Yeah, sorry, I didn't get time to think my questions through. The first was on your differential analysis, do you offer any kind of weighting? Yeah, sure, my site sucks on IE6, but I really don't care because it's just a few bots in China or something like that.
It'll automatically kind of weigh that stuff for you just by the volume of traffic, because if you're having another problem, that's going to bubble up to the top. But there's no real way to say, I don't care about IE6. But you can say, I care about these different requests. Like these request types, I'm very interested. Like I'm very interested in checkout. I don't really care as much about this other one over here.
And my second question is a little bit harder, and that is, most of the time I spend my time, I know there's a problem. I first have to figure out when that problem started happening, and then find what that's correlated to. So have you thought about those trend break detection, things like that?
Yeah, so most of the performance differential stuff is really focused on the real-time scenario, what's happening right now. So if something gets fixed and resolved, it's going to start bubbling down. But the investigate workflows are designed more for you can go back in time and look. So I can say, what happened yesterday between noon and 2, because I know there was a problem. Let me zone right in on that, and maybe even compare it to what happened before. Now, we do have some comparison views. So you could say, last week versus this week. But in general, if you start looking back very far in time, that investigate is the path to go.
I think it's a good point, though, that time really is another dimension, just like any other that we're tracking here. And I don't think we're done on that front. I think looking at changes in correlated behavior over time would surface things that we're not surfacing right now through this approach. I think that would fall into the bucket right now of where the human is helping fit the data. But there's definitely an opportunity there. It's a great question.
Thanks.
What kind of storage system do you use?
What kind of storage system do we use?
Oh, what kind of storage system? It's a NoSQL backend, essentially. We started off, following the MapReduce pattern, back about 10 years ago. So it's it puts a lot of the storage engine that we have is essentially a columnar database. Provides that level of compression. That's also important because that gives you, when you store in a columnar way, you have a very, very clear sense of what your dimensions are, what the variability of values are within those dimensions. It gives you a lot of the metadata kind of inherently from that structure that you need to drive this kind of analysis. Sure. This is one that we built originally. We are evaluating other technologies to see if we can leapfrog ahead to do some more things in the future. But the storage backend we have right now, we've been using for about 10 years. It originally started as an on-premise solution, similar to a T-Leaf in some ways, but more performance-oriented than user experience-oriented. So we have a lot of DNA about storing large data sets, and that's the same technology that's powering our SaaS now.
You're talking more like SLA reporting rolled up for like a week, that kind of thing? Yeah, so we actually have a reporting section specifically designed for that. I mean, come by the booth, we can walk you through the full demo. We're focused in this conversation exactly on the performance differential, but yeah, there's reports for SLAs in there.
Yeah, I mean, one thing to add on that is a lot of performance reporting that we do is oriented towards information that we're providing to others. We're trying to inform the business how well our infrastructure is doing. I kind of see that as a separate category of analytics in a way. What we're showing here is really not business metrics, right? We're not talking at this level about let's model your revenue and put the revenue correlated against. There are opportunities for that. And it's not that we're turning our back on that, but what we're really trying to focus on in this presentation is what do performance engineers doing the optimization need to understand about their systems. That is a huge problem. It really hits home for us. We have a lot of history about doing kind of business level metrics, business level reporting. So we feel like that's fairly well covered ground. But analytics that really focuses on the technical performance is something that we feel like it will really speak to this audience.
Actually, what I mean to say is, for example, right, it's not like we really draw a conclusion, we really try to incur some action, right? So the conclusion makes sense to bring to that meeting, saying what improvement or what we face, right? Essentially. So how that makes sense in terms of performance side, go to a meeting, how that should be, how you guys.
Yeah, exactly. The one thing we didn't talk about here that I talked at Glue last month, and this was a larger focus of that talk, but about emergent complexity, and the idea that as a technologist, you're going to start building something that's very simple, that you can understand. You can carry the infrastructure in your head. You can carry the architecture diagram around with you on your phone or whatever. As that moves to be more and more real, what we see for most of our customers is the complexity goes sideways on you. And I made the point at Glue that if you want to start, if you have something that's simple and you want to keep it simple, keep it in the lab. Don't let it out in the real world, right? Because as soon as it gets out in the real world, you're going to have investors, you're going to have partners, you're going to have affiliates, you're going to have customers. All these people are going to be making unique demands on you, and it's going to be up to you to somehow fix all of that. So the idea that we can start by picking a certain set of technologies that will permanently stave off complexity is something that I've come to not believe in, as much as I like looking for silver bullets as much as anybody else. So I think that's really the preeminent problem that we see is as you're scaling your business and as you're bringing that website out into the real world, how do you deal with the real world complexity that results from that? Whether that's elastic computing or traditional computing, it gets incredibly complicated incredibly quickly. The business people are always going to want to see that reduced to service levels, to easy to understand metrics. And the same way that technologists want to try to reduce that operating system down to something simple that we can carry around in our heads. But that's not really the reality of what ends up coming in the marketplace, especially if you're successful.
Well, I think we're out of time. So thanks for coming. We'll stay here for a few more minutes. So you can come down and have any other questions, and come by the booth, too. Thank you. Good. Good.